Hello, my name is David Padgett, and I'm an engineer at Vadum Incorporated in Raleigh, North Carolina. Anti-ship cruise missiles represent a threat to naval assets around the world. One of the elements of the Navy's layered defense against anti-ship cruise missiles is the use of guided missiles to intercept ASCMs. Vadum is working on two technologies designed to make this process more efficient. The algorithms I'll talk about in this set of charts involve improving the performance of one guided missile against a single anti-ship cruise missile threat. The other technology I'll present in this forum aims to improve the performance of multiple shots against multiple incoming ASCM threats. If you're interested in seeing if these technologies can help your combat system improve its missile defense capabilities, please either talk to me during this event or reach out to me using the contact information at the end of this brief. Vadum Incorporated is a group of about 40 engineers located in Raleigh, North Carolina. The company has worked on a wide variety of programs in the defense world over the years, but our main areas of growth right now are algorithm development in the electronic warfare and sensor data exploitation spaces. Our recent transition successes have been in the electronic warfare algorithm area, where we've developed machine learning algorithms capable of online characterization of unknown radio frequency emitters. These technologies improve the electromagnetic self-defense capabilities of the FA-18, the mission performance of the EA-18, and the Army's ability to do electronic warfare battle damage assessment. We also have an active hardware group that's in the process of transitioning an explosive ordnance disposal device which provides multi-shot capability while mounted on a robot arm. We'd like to make the technologies we're briefing at this event our next major transition success. The Navy must protect its assets against anti-ship cruise missiles. ASCMs use evasive maneuvers to increase their own survivability. We're working with the Navy to develop algorithms to improve guided missile engagements against maneuverable ASCMs. The improved performance margin can be used either to increase the effective missile battle space or to unlock latent capabilities of our current missile systems against advanced cruise missile threats. The first transition landing pad for this technology is the AEGIS Combat System installed on Arleigh Burke-class destroyers. The Navy is investing in studying the ASCM problem because the world of anti-ship cruise missiles is changing rapidly. ASCMs are getting better in a number of ways, including becoming more maneuverable and thus more survivable. Traditional guided missile algorithms rely on an interceptor being much more maneuverable than the missile it's trying to intercept. Sometimes a maneuver overmatch of 3 to 5 times is required to intercept a maneuvering threat. This means that if an adversary doubles its maneuverability, we have to increase ours by a factor of 6 to 10 to maintain performance, and this is an expensive proposition. Vadum is investigating missile guidance algorithms which can exploit some of the properties of ASCMs to reduce this required maneuver overmatch. While the first transition platform for this technology is the AEGIS Combat System, we've identified several other potential candidates for transition, which represent systems responsible for cruise missile defense. These include the Navy's Ship Self-Defense System, the Future Frigate Program, and the AEGIS BMD mission. Other platforms for potential transition in the DoD include the Patriot Missile System and the Missile Defense Agency's Hypervelocity Projectile Program. If you're here on behalf of any of these programs, or any other program responsible for missile defense, we'd like to talk to you about how our technology can help you meet your current and future requirements. The algorithm that we've developed is called Trajectory Prediction for Air Defense, or TPAD. It's a guided method based on predicted intercept points, or PIPs. Traditional missile guidance methods react to a target's maneuvers as the engagement unfolds. When engaging maneuvering ASCMs, this leads to unnecessary missile reactions to the ASCM maneuvers. Each of these reactions burns up missile energy. A PIP-based system predicts where the ASCM will be in the future and guides the interceptor on an efficient path to that point. The TPAD algorithms develop a PIP by constantly comparing the incoming ASCM trajectory to an internal model database. These models can codify intelligence estimates of potential trajectories, kinematic missile models evaluated in real time, or other prediction schemes. TPAD determines which models are good matches to the observed ASCM behavior and uses a weighted combination of these models to develop a prediction of future ASCM behavior. TPAD then uses the expected future behavior of the threat, combined with weapon capabilities and doctrine, to determine the best places to attempt to engage the threat. The TPAD prediction framework is capable of not only generating predictions of ASCMs, but also of real-time self-evaluation. It's also extensible to new models that become available either through threat updates from the intelligence community or observations made during actual engagements. Vadum is currently working with Lockheed Martin to drive towards a TRL of 5. Our current period of performance takes us through August of this year and involves Vadum integrating TPAD into a high-fidelity Lockheed Martin model of the AEGIS Combat System. At that point, PEO-IWS has an option to continue development for another year. The current plan for this option phase is to integrate TPAD into a government reference model of the AEGIS Combat System for future evaluation. If these evaluations are successful, PEO-IWS will work with Vadum and Lockheed Martin to develop a path to integrate TPAD into the AEGIS Combat System. As of now, TPAD's competition is current missile guidance algorithms in the AEGIS Combat System, and we're unaware of other similar approaches in the missile guidance space. TPAD has some aspects that make it an attractive addition to cruise missile defense algorithms and weapon systems. The first is the fact that it uses a framework architecture that's extensible to new information. The models that drive the system can be changed out fairly easily as new information becomes available. The offline training process that we use to develop the models that go into the system allow for intelligence data about potential threat trajectories to inform a missile guidance solution. It's easier to hit a curveball if you know what a curveball looks like. However, TPAD is also designed to degrade gracefully. If a PIP resulting from TPAD calculations is unlikely to be a quality PIP, its self-monitoring functions will send a signal to the weapon system that this is the case, and that it can use an alternative missile guidance solution if one is available. The self-monitoring function also allows online performance improvement. Threat trajectories that are not good matches to any of the resident models can be saved as new models themselves, allowing TPAD to quickly ingest and use new knowledge about threats it may have to engage. Transition to the fleet will occur after extensive evaluation of TPAD in both Lockheed Martin and independent government models of the AEGIS Combat System. The rest of the Phase 2 program will be devoted to gathering high-quality data about TPAD performance, which will be reviewed both by PEO-IWS and by Lockheed Martin in their role as AEGIS Combat System engineering agents. Post-Phase 2 activities will involve determining the right path to get into the AEGIS Common Source Library and then into tactical weapon system implementations. While there is a defined transition path to the AEGIS Combat System, we believe that our partnership with Lockheed Martin will let us practice transitioning this technology to other platforms as well. Other transition targets, like other AEGIS baselines, other Navy, or other DoD missile defense systems, will benefit from this practice on third-party transition that Vadum is gaining now. The TPAD interface is being developed and integration exercises being performed burn down the risk for transitioning TPAD to other platforms in the future. The reason that we're here today is to start conversations with people outside of the AEGIS community who are interested in seeing how TPAD can help them meet current and future requirements. If you're interested in seeing what TPAD can do for you, please visit our virtual booth or contact me using the information below to start discussions on how we can work together.